So the next video is going to be on inverse reciprocal trig expressions. So this is going to be on secant, secant theta, cosecant theta, and cotangent theta. So we got introduced to these in the previous unit and how they are the reciprocals of cosine, sine, and tangent. So it gets a little more confusing here because now we said don't treat them as reciprocals, but now we're looking at the inverse of the reciprocals, okay? But luckily they have close ties with their counterparts. So let's start with secant. So the reciprocal of secant is going to be cosine. So just recall that cosine theta is equal to 1 over secant theta, or secant theta is equal to 1 over cosine theta. So they are the reciprocals of one another. Now, if we think about arc cosine, I have arc cosine, and for cosine, the input for the inverse cosine is going to be the x-coordinate on the unit circle. We talked about this pretty extensively in the previous video. And it's going to be equal to some type of angle. Now, when we talk about arc secant, we can flip these. So if I go from arc cosine to arc secant, I'm taking the reciprocal, okay? So if I take arc secant and I'm using the same input, I'm using the reciprocal of cosine, which means the input will also be reciprocated. Because if you think about it, for secant, when we talked about just secant theta, it's the reciprocal of cosine, therefore the output was the reciprocal of the x-coordinate, so it was 1 over x instead of just x, because cosine theta is x. So we're going to use this same principle for arc secant. Like for every example that has arc secant, I end up flipping it to arc cosine, just because it's a more familiar world or realm of what that input will look like, okay? So for arc secant, we do have to talk about a couple of things. For secant, we're not going to draw the sketches. We used to, but again, limitations based on the number of topics we're discussing. As far as the restriction for domain and range, if you think back to secant, it's going to look something like this. And because it's the reciprocal of cosine, the range is going to use all the values that cosine did not, except for +1 and -1. So the range for secant is -infinity to -1, union 1 to infinity. And if we take a look at the diagram above, we have a restriction, okay? It is from 0 to pi. This is a diagram for arc secant, or the inverse of secant, but with that range, we can see that the domain of secant is restricted from 0 to pi, inclusive. And I can see that it's in quadrants 1 and 2, which is very nice because this is the same as arc cosine. So arc secant and arc cosine are going to share the same quadrants, quadrant 1 and quadrant 2. So if we think about the domain for arc secant, it is going to be the range of secant, which is -infinity to -1, union 1 to infinity. And then the range with that restriction is going to be from 0 to pi, inclusive. And then everything that I just talked about with cosine and secant, the same applies for sine and cosecant, okay? So again, if I have, say I have arc cosecant. Now arc cosecant, we're gonna just call this input y, all right? Because it deals with the y coordinates on the unit circle. And our output will be some type of angle. In the you're going to have calculator examples where there's no cosecant button, therefore there's no arc cosecant button, but there is an arc sine key, okay? So we're going to switch arc cosecant to arc sine, but when we use the reciprocal, we're also reciprocating the input. And that'll be something that we do in a couple examples with the calculator. But the same relationship exists as we talked about for cosine and secant. So if we think about cosecant, just regular old cosecant. Cosecant has a vertical asymptote on the y-axis, and then the curves existed like such, okay? So the range for cosecant is the same as secant. It's from negative infinity to negative 1, union 1 to infinity. And if we take a look at the diagram, it also has the same restriction as arc sine. So this is the range for arc cosecant. Therefore, it is the domain for cosecant. I think I said arc secant. I meant arc cosecant. So the diagram shows the range for arc cosecant, which means it's going to be the domain restriction for cosecant, which is negative pi over 2 to pi over 2. And it is inclusive. So that means for arc cosecant, the domain is going to be what the range was for cosecant, which is negative infinity to negative 1, union 1 to infinity. And then the domain is going to be the range, which is negative pi over 2 to pi over 2. So quadrants 1 and 4. So again, arc cosine and arc secant both share quadrants 1 and 2. And then arc cosecant and arc sine share quadrants 1 and 4. Now we have the ugly stepsister of the group, tangent. Arc tangent and arc cotangent are the only reciprocals that do not share quadrants, okay? So with arc tangent, there are a couple things we're going to have to remember when we switch from arctan to tangent, or arctan to arc cotangent, which we'll talk about those as we do problems. But for now, I just want to talk about the domain and range of cotangent. So for this one, for regular old cotangent, cotangent has a domain of, it used to be that domain restriction, x cannot equal pi k. But now if you look, this is the range restriction for arc cotangent. Therefore, it will be the domain restriction for cotangent, which is from 0 to pi. Now, just like tangent, this is going to be encompassed in between two asymptotes, so it'll be non-inclusive. And then the range is going to be all reals. So if you think about cotangent, it looks like this. Had vertical asymptote on the y-axis, and it is decreasing. So all reals because it's going from negative infinity to positive infinity. Now, arc cotangent, we're going to flip the domain and the range. So the domain will be all reals, and then the range will be 0 to pi, non-inclusive. All right, so I'm going to skip this part because it's mainly, this is more about equations, trig equations, which is going to be a separate unit. So I just want to focus on evaluating the expressions below, okay? So we have arc secant of negative 2 root 3 over 2. All right, this is a pretty heavy first example. I should have chose one that was a little less aggressive, but we can get into it. So if we think about arc secant, I want to use its reciprocal. I'm more familiar with the unit circle using cosine rather than secant. However, if we think about secant, we can flip to arc cosine, but when you use the reciprocal of this inverse trig, it's also going to reciprocate your input. It will not negate it. If it starts negative, it stays negative. If it starts positive, it stays positive. So we end up with negative 3 over 2 root 3. And these are equivalent, okay? So we can go ahead and use the equal sign. Now, this is arc cosine, which means I'm focused on the x-coordinate from the unit circle. So this is technically going to be x from the unit circle. Not just the bottom, the entire term in there. So x from the unit circle, which means if we go back and look at arc secant, this is technically 1 over x from the unit circle. And this is why we switch back to arc cosine, is because thinking about 1 over x on the unit circle requires a little bit more manipulation. We want to try and minimize the manipulation, okay? Especially because there's already so many moving parts. Make it easier for yourself. So this is 1 over x from the unit circle. All right, so now we're back to what we did in the previous topic, all right? But there's still some manipulation we have to do. The next question is this a standard coordinate on the unit circle? The answer is yes. And if you weren't sure, hopefully seeing that root 3 and a 2, hopefully that's kind of scratching your brain and like, okay, that's giving me like root 3 over 2 or something like that, okay? So sometimes you're going to have to do rationalizing, which we don't normally do. But in order to evaluate the standard angle, we're going to go ahead and rationalize this. So we'll multiply this with root 3 over root 3. Rationalizing, I want to get the radical out of the denominator, so I'm going to multiply it with itself. But if I multiply the denominator, I also have to multiply the numerator because I need to keep the same weight. Root 3 over root 3 is technically 1, so I'm not changing the weight of this input. So now we're going to end up with negative 3 root 3 over 2. Root 3 times root 3 is going to be 3. And if we look at this, the 3's cancel out, so we end up with negative root 3 over 2. So this is a standard coordinate from the unit circle, okay? So this would be a non-calculator problem. So arc cosine exists in quadrants 1 and 2. And now this is taking us back to what we did in the previous topic. This is a negative x coordinate, which means I will be in the second quadrant. And we are actually further away from the y-axis. And that corresponding angle is going to be 5 pi over 6. So that means if we go back to the beginning, that means arc secant of negative 2 root 3 over 2 is equal to 5 pi over 6. If you did this as arc, if you kept it as arc secant and you're comfortable with flipping 1 over x, then you would be working with negative 2 over root 3. That's rare. I don't see a lot of students utilize that. They usually switch to arc cosine, but you don't have to. You're not required to go to this step, although it is typically more helpful. All right, arc secant of 1/2. So going back to what this problem was, with arc secant, this is going to be 1 over x on the unit circle, okay? So there's a couple ways to approach this. If we switch it, we can do arc cosine of 2 over 1, or it's just 2, okay? Now this is the x coordinate from the unit circle, okay? But there's a problem. If you think of the unit circle, the radius for the unit circle is 1. Or negative, well, the radius is 1, so the x coordinates are 1 or negative 1 to 1. That is your domain restriction for arc cosine, negative 1 to 1. So we can't do 2. So therefore, this is undefined because it's out of the domain for arc cosine. But if you remember the domain for arc secant, it's negative infinity to negative 1 union 1 to infinity. And that 1/2 is also not within the domain. So this is undefined. So if you were to type this in the calculator, you would get error. So again, that's a fail-safe for you. But you do need to remember the domain restrictions for all 6 of these. So therefore, undefined because it's out of the domain. All right, arc cosecant of negative root 2. So this is a newer one. We were working with secant. So the reciprocal for cosecant is sine. So let's do arc sine. And then we will reciprocate the input, which is negative 1 over root 2. So this is technically a y-coordinate on the unit circle. And we don't see this one a lot. You'll see it more in calculus, if you plan on taking calculus. If we rationalize this, we end up with our root 2 over 2. So we have negative 1 over root 2 times root 2 over root 2. So we get negative root 2 over 2. So this is family of 4s. So it's either going to be pi over 4 or negative pi over 4. And that's because arcsine only exists in quadrants 1 and 4. So this will either be pi over 4 or negative pi over 4. And for sine, it's y, so we're going to be going down. Therefore, it's going to be equal to negative pi over 4. And you can check all of these in the calculator. We'll go ahead and start with this one. So if I go to the calculator and I will do, hopefully it loads. There we go. All those ads are going to start popping up. Yep, I called it. Let me try Xing them out. You X them out once and they go away, but it did not used to be that bad. So we have, I believe it was arc cosecant, but I don't have an arc cosecant key, so I'm going to use arc sine. So I'll do second sine, and then my input was negative root 2, but it's going to be negative 1 over root 2 since we have to reciprocate the input. And I get negative 0.785. So my exact radian was negative pi over 4. So let's do negative pi divided by 4. Whoops, that's a weird one. And I get the same decimal, so negative 0.785. So you can quickly check all of these. It's not an exact in the calculator, but you can see the decimal approximation for your exact radian and the decimal approximation for your inverse trig expression. So that's a nice way to double check. All right, so now we have arc cotangent of negative 1. I would put a red flag by this one, literally, or a big star or something. This is a very special case, very unique case, and one that, as much as I talk about it, students typically overlook it in a testing situation and sometimes on the AP exam. Okay, so yes, it's arc cotangent, and then with cosecant and secant, we always switch to sine and cosine. I would get comfortable with cotangent and its negative values, especially if it looks like it's a standard form on the unit circle, okay? But there are going to be times that you do have to switch. You won't have an option but to switch, okay? And we'll see one of those in a second. Now, for arc cotangent, it exists in quadrants 1 and 2. Remember, it's not going to be the same as arc tangent. And this coordinate here is x over y on the unit circle. Because tangent is y over x, its reciprocal cotangent will be x over y. Okay, so if I'm thinking of negative 1, whenever I see negative 1 or positive 1 for tangent, you should be thinking of root 2 over 2, okay? Because those are the only coordinates on the unit circle that share a point. Therefore, the ratio will be root 2 over 2 divided by root 2 over 2, so it's going to be 1. Now, the difference is this one's negative, which means one of the coordinates is negative. In quadrant 1, they are both positive. Therefore, that would be a positive 1. In quadrant 2, the x-coordinate is negative and the y-coordinate is positive. Therefore, the result will be negative 1 if we take those ratios. So in quadrant 2, our answer for this is theta equals 3 pi over 4. So arc cotangent of negative 1 is 3 pi over 4. But what if we did switch to arc tangent? So let's go ahead and see what that looks like. So I'm going to switch to arc tangent. And if we reciprocate it, it's still going to be negative 1. Okay. Now here's the issue. Arc tangent exists in quadrants 1 and 4. Okay. That's a problem because whenever we switch, we have to keep to the true expression. We have to stick to the restrictions of arc cotangent, which is quadrants 1 and 2. But when we switch to arctan, we now have 1 and 4. Arc cotangent does not exist in quadrant 4. So anytime that we get a negative coordinate for arc cotangent, we have to somehow get it out of quadrant 4 and into quadrant 2. So say that I'm at -1. That's the -1 here. I need to find a way to get it to the -1 that's in quadrant 2 so that it exists within the realm of arc cotangent. And how do we do that? You add pi. So if you have a negative input for arc cotangent and you switch to arctangent, you're going to have to add pi. So if we stay in arctangent of -1 is going to be -pi/4 because it's in quadrant 4. And then because we're dealing with arc cotangent originally, we have to add pi. So we get -pi/4 plus pi. I just rewrote the same thing. I meant to rewrite it as 4pi/4, so they have a common denominator. -1 plus 4, we get 3pi/4, which takes us back to what we got when we just remembered what cotangent was. So if it's a standard angle, staying in arc cotangent will be in your best interest. Otherwise, you're going to switch to arctan, and just remember you have to add pi. Now, for a calculator, it's unavoidable, but it's a lot simpler if you're getting a decimal radian. All right, let's look at arc cosecant. So we have arc cosecant, and this is definitely going to be this is definitely a calculator because this is technically 1/y on the unit circle, but there is no -4 on the unit circle unless we increase the radius, which when we do that, it's no longer a unit circle. So I'm going to switch to its reciprocal sign. So if I reciprocate the inverse trig, I also have to reciprocate the input. So this is going to be a calculator question. All right, so we'll switch to the calculator. Wrong calculator, I don't like that one. And all the adds are back. Okay, so we are doing arc sine, so second sine, and it was of -1/4, so I'll do -0.25, close it off, and we get -0.252. So we get -0.252. Did we do this one already? I feel like we did. Oh, we did. We did it on the calculator. Why is that back with the... Okay, interesting. I need to switch that up too. Oh, but it's a different form. Okay, that's a good connection then. So yeah, we did do that one, but we started with arc sine. Okay. All right, here's the last one. Arc cotangent of √3/2. Here's another tricky one. So √3/2 is on the unit circle, but it is specific to sine and cosine. Cotangent does not have a coordinate that is √3/2, okay? So this is definitely going to be a calculator question. All right, so for arc cotangent, the domain is all reals. So whatever you type in the calculator, it is going to be, you're going to get an output or an angle. All right, but there's no cotangent key, so we are going to have to use the reciprocal. So we have arctangent, and we have to reciprocate the input as well, 2/√3. All right, going to the calculator, I have second tangent, and then we have 2 divided by the square root of 3. And we get the decimal 0.857. Now, if you're thinking, okay, but aren't you supposed to add pi? With this one, we don't have to. So again, arc cotangent exists in quadrants 1 and 2, and then arctangent exists in quadrants 1 and 4. They share this quadrant. They share quadrant 1. So whenever you switch to arctangent, and it's a positive input, there is no adding pi when you're in quadrant 1. Okay. But now let's try this one. Let's try arc cotangent of -√3/2. And let's see what happens. So again, this is not on the unit circle. So we are going to have to use the calculator. There's no cotangent key. So we have to flip to arctangent. So I have arctangent of -2/√3. This is a negative input. So now I'm in the fourth quadrant, which arctangent does not exist in. So now I have to add pi. This is going to take me from the fourth quadrant. This will take me from the fourth quadrant to the second quadrant whenever I add pi. Okay, that's why we don't do it in quadrant 1, because they both share it. So if we go to the calculator, maybe, there we go. All right, so we're going to have inverse tangent of negative. We'll have 2/√3. And the add pi should go on the outside, not on the inside, because then you're changing your input, which we should not be doing. And we get 2.284. So this one would be 2.284 for arc cotangent. All right, the next video will be on composites with inverse trig functions. Hope this helps.